Welcome back. Collisions and impulse are fundamental concepts in physics. In this video, we will understand how objects interact and transfer energy during collisions. A collision can be either elastic or inelastic. In an elastic collision, both momentum and energy are conserved. The colliding bodies bounce off each other, without any permanent deformation or generation of heat, meaning there is no loss of energy during the collision. In contrast, an inelastic collision involves some loss of kinetic energy, which is transformed into other forms of energy, such as heat, sound, or deformation. In such collisions, the colliding bodies may stick together, or become deformed. In both elastic and inelastic collisions, momentum is conserved, as long as there is no external force acting on the system. However, a collision can be influenced by external forces. When external forces are present, the momentum of the system is not conserved. Instead, the change in momentum of the system is determined by the external forces acting on it. Newton's second law of motion states that the rate of change of momentum of an object is directly proportional to the net external force acting on it. The change in momentum of a system, subjected to external forces, is given by the product of the external force and the time duration over which it acts. This relationship is expressed by the impulse-momentum theorem, which states that the change in momentum of an object is equal to the impulse applied to it. The impulse is the product of the applied force and the duration of time over which the force is applied. Alright, with that introduction, let's look at the first example. A ball with a mass of 80 kilograms collides with a wall at a velocity of 70 meters per second and at an angle of 30 degrees to the wall. After the impact, it travels at a velocity of 50 meters per second and at an angle of 15 degrees to the wall. We need to find the impulse of the collision. Additionally, if the collision lasts for 15 milliseconds, we need to determine the force exerted on the wall. First, let's identify the XY reference frame. Next, we will resolve the initial and final velocities into their x and y components, as illustrated in the table. This involves determining the horizontal x and vertical y parts of each velocity vector. By referring to the xy coordinate system, we can accurately assign the appropriate positive or negative sign to each component based on its direction. To find the impulse, we need to determine the change in momentum in both the x and y directions. Let's first consider the x direction and calculate the change in momentum. We start by identifying the initial and final momentum in the x direction, denoted as m times v sub ix and m times v sub fx. The change in momentum in the x direction is then found by subtracting the initial momentum from the final momentum. Simplifying this gives us the change in momentum in the x direction as minus 986 kilograms times meter per second, which represents the impulse in that direction. Similarly, we can find the impulse component in the y direction by considering the change in momentum in this direction. By identifying the initial and final momentum in the y direction, and subtracting the initial momentum from the final momentum, we can simplify to find the impulse in the y direction, as minus 3,835 kg times meter per second. Both impulse vectors are in the negative direction of the xy coordinates. It is important to remember that this represents the impulse on the ball. The vector sum of the impulse of the ball can be expressed by combining its components. Given the components jx and jy, we calculate the magnitude of the resultant vector by taking the square root of the sum of the squares of these components. This gives the magnitude of the impulse vector as approximately 3,959 kilograms times meter per second. The direction of the resultant vector is determined by the angle it makes with the negative x-axis, which can be found using the inverse tangent function. The angle is approximately 75.6 degrees, indicating that the impulse is directed predominantly in the negative y direction, with a significant component in the negative x direction. According to Newton's third law, the impulse on the wall is in the opposite direction to the impulse on the ball. The xy components of this vector and the resultant vector are shown on the screen. Now, with this information, we can find the magnitude of the force applied on the wall. Given the duration of the impulse is 15 milliseconds, we can use the following expression to calculate the force on the wall due to the impact of the ball. The magnitude of the impulse is approximately 3,959 kilograms meter per second, and the duration of the impulse is 15 milliseconds. Using these values, we can work out the average force on the wall as 264 kilonewtons. The direction of this force is the same as the direction of the impulse. What you can take away from this is that when the duration of the impact is longer, the force on the wall will be less, compared to a scenario where the duration is shorter, even though the impulse is the same. This means that when the surface is hard, the impact lasts for a very short time, resulting in a higher force, as opposed to a surface which is soft, where the impact duration is longer, resulting in a lower force. Before we move on to the next example, I want you to consider whether this collision is elastic or inelastic. I assure you that you will be well acquainted with how to answer this question by the time you finish watching this video. Alright, let's move to the next example. This is similar to what we just did, but instead of looking at one object colliding with a wall, we are going to look at multiple objects bombarding a wall. Without further ado, let's look at the question. A dispenser fires cannonballs at a rate of 100 cannonballs per second, straight at a wall. Each ball has a mass of 25 grams, and is fired at a speed of 800 meters per second. We need to determine the average force on the wall. First, let's convert the mass of each cannonball to kilograms for consistency in units. Next, we will calculate the change in momentum of one cannonball. Before doing so, we will establish a reference frame to ensure that we obtain the correct signs for the velocity and momentum vectors. The change in momentum in the x direction is given by the following expression. By substituting the values, we find the momentum of the ball to be 20 kilograms meter per second. The force applied to the wall is given by the rate of change of momentum. Since the dispenser fires at a rate of 100 cannonballs per second, the rate of change of momentum is calculated by multiplying the change in momentum of a single ball by the number of balls colliding with the wall each second. Substituting the change in velocity and the number of balls striking the wall each second results in a force of 2 kilonewtons, which is the force applied to the wall. In the first example, we calculated the force applied to the wall due to an impulsive force, considering the rate at which the impulse was applied. In the second example, we calculated the force applied to the wall by examining the rate of change of momentum in the direction of the force. In both cases, the key concept is that the force exerted on the wall is determined by the rate at which momentum changes, whether due to a single impulsive impact or a continuous stream of impacts. If this point is clear, we can move on to the next example. In this example, a 6 kg spear is stopped by a 10 kg wooden block. If the spear is hurled at 200 meters per second, we need to determine how fast the wooden block, pierced by the spear, will move. To solve this problem, we will use the principle of conservation of momentum, which states that the total momentum before the collision should be equal to the total momentum after the collision. The initial momentum is the momentum of the sphere, which is the product of its mass and its velocity. The final momentum is the momentum of the combined sphere and wooden block. The total mass of this combined set is 16 kilograms. If we assume the final velocity to be u meter per second, then we can write the final momentum as 16 times u. According to the principle of conservation of momentum, the initial momentum is equal to the final momentum. By equating the two expressions, we can calculate the speed of the combined unit to be 75 meters per second. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. Before we proceed to the next question, let's understand the principle of energy conservation. I will briefly explain the principle, so we can attempt the examples in this video, and in a subsequent video, I will discuss this principle in detail. The principle of energy conservation states that the total energy of an isolated system remains constant over time. Note that energy cannot be created or destroyed, it can only be transformed from one form to another. This principle is fundamental in physics and applies to all types of energy, including kinetic energy, potential energy, thermal energy, and so on. However, in this section, we are concerned only with mechanical energy. Mechanical energy comes from an object's position and movement. It is the sum of kinetic energy and potential energy. So, when you add an object's potential energy to its kinetic energy, you get mechanical energy. The energy possessed by an object due to its motion is called kinetic energy, and it is expressed by this equation, where m is the mass, and v is the velocity of the object. The energy possessed by an object, due to its position or configuration, is called potential energy. If this stored energy is due to gravity, it is called gravitational potential energy, which is given by the equation, where m is the mass, g is the acceleration due to gravity, and h is the height above a reference point. If this stored energy is due to tension in a spring, it is called elastic potential energy, given by the equation, where k is the spring constant, and x is the displacement from the equilibrium position. When an object's potential energy is combined with its kinetic energy, the total is called mechanical energy. This combined energy helps explain how objects interact, move, and exert forces within a closed system. With that understanding, let's look at the next example. A ball with a velocity of 10 meters per second strikes an identical stationary ball. After the collision, each makes an angle of 30 degrees with the original line of motion. We need to find the velocities of the two balls and determine if the kinetic energy is conserved in this collision. The principle of conservation of linear momentum applies to both elastic and inelastic collisions, provided the system is isolated. A ball moving at 10 meters per second hits a stationary ball, and after the collision, both balls move at an angle of 30 degrees from the original direction. To simplify the analysis, we decompose their velocities into components parallel and perpendicular to the initial motion. These velocity components can also be resolved in any orthogonal direction if desired. Next, we will apply the principle of linear momentum in the initial direction of motion. The conservation of momentum before the impact is 50 kilograms meter per second, given by the product of the mass and velocity of the moving ball. After the impact, the momentum is distributed between the two balls, each moving at an angle of 30 degrees to the initial direction. The conservation of momentum equation after the impact is given by this expression. Since momentum is conserved before and after the impact, we can equate the two expressions. We will arrive at this expression with v sub 1 and v sub 2 when we apply the conservation of momentum in the initial direction of motion. We will repeat the process in the orthogonal direction. The initial momentum in this direction is 0. However, considering the conservation of momentum in the y direction, we can write this equation. As we did before, we can equate the two expressions since momentum is conserved before and after the collision. This simplifies to v sub 1 equal to v sub 2, indicating that the final velocities of the two balls are equal. Using these resolved components, and the conservation equations, we can determine the final velocities of both balls after the collision. Now that we have the initial and final velocities of both balls, we can determine whether this collision is elastic or inelastic. First, we will find the total energy of the system before the impact. In this case, there is no potential energy, because the motion of both balls is confined to the same plane. So we only have kinetic energy. This is given by the following expression before the impact. Next, we will calculate the system's kinetic energy after the impact, which is the sum of the kinetic energies of both balls. Wait a minute. Why do we have two different values for kinetic energy? Why is this not an elastic collision? To find out the reason, let's repeat the same exercise. But this time, we will consider the angle that the colliding ball makes, with the initial direction after the collision as theta, and find the values for theta, and the velocities of the two balls after the collision. As the first step, we will apply the conservation of momentum in the initial direction of motion. This will give us the following expression. Next, we will apply the conservation of momentum in the orthogonal direction to the initial direction of motion, or in the y direction. Suppose there is no energy loss during the collision. We can assume the total energy before the collision is equal to the total energy of the system after the collision. Based on the reference plane chosen for the system, we can consider the potential energy to be 0, and apply the principle of energy conservation, taking into account the kinetic energy before and after the collision. This leads to the following expression. We are left with three equations and three unknown variables: the velocities of the two spheres after the collision v sub 1 and v sub 2, and the angle theta. To eliminate theta from the first and second equations, we can square both equations and then sum them. Since the sum of the squares of sine theta and cos theta is equal to 1, a basic trigonometric identity, we can derive a fourth equation that no longer contains theta. By subtracting this fourth expression from the third expression, we can rewrite the equations as a quadratic equation in terms of one unknown, v sub 1. When we solve this quadratic equation, we obtain two possible values for v1. In this situation, v1 is not 0, so we rule out the possibility of v sub 1 equals 0 meters per second, and choose the second value, which is 5 times the square root of 3. We ruled out the possibility of the velocity of the ball with which the collision occurs being 0, because it would imply that the ball did not move at all after the collision. This could only happen if there was no collision, or if the ball missed its target entirely. However, since the problem assumes that a collision does occur, we must consider the scenario where both balls interact and exchange momentum. It's important to consider the specific circumstances and physical context of the problem, rather than blindly applying principles like momentum and energy conservation. This ensures that the analysis is accurate and relevant to the situation at hand. Now that we have determined the velocity of one ball after the collision, we can find the velocity of the other ball, using the third equation. After performing the calculation, the velocity of the second ball comes out to be 5 meters per second. Next, we need to determine the angle of deflection, theta. To do this, we can use either the first or the second equation derived from the conservation of momentum. By using the second equation, we find that the angle theta is 60 degrees. An interesting observation is that the sum of the deflection angles of the two balls adds up to 90 degrees, meaning that the two objects move away from the collision point at right angles to each other. This outcome is not a coincidence, but a well-known result in the study of collisions. In an elastic collision between two objects of equal mass in two dimensions, the objects will always separate at right angles after the collision. This is due to the conservation of both momentum and kinetic energy in elastic collisions. The kinetic energy and momentum are distributed between the two objects in such a way that they move in perpendicular directions, resulting in a 90-degree separation angle. In contrast, when the separation angle between the two objects after a collision is not 90 degrees, it usually indicates that the collision is inelastic. In an inelastic collision, some of the kinetic energy is converted into other forms of energy, such as heat or deformation, and the objects do not necessarily move at right angles to each other. The fact that the separation angle was not 90 degrees in the previous scenario indicated that the collision was inelastic. However, in this current example, the separation angle is exactly 90 degrees, confirming that the collision is elastic, where no kinetic energy is lost, and the objects move away from each other at right angles. I hope this explanation was clear. Okay, let's move on to the next example. This will be the last example in this video. I'll be uploading more videos on this topic in the coming months, so stay connected to get notified when I release new content. A ball of mass mkg is suspended by a weightless rod of length L meters. Another ball of mass 2 mkg collides horizontally with the ball of mass m at a speed of u meter per second, such that the ball with mass m completes a vertical circle, as shown on the screen. We need to find the initial speed of the ball with mass 2m before the collision, so that the ball with mass m just manages to complete one full circle. For the sphere to complete one full circle, the velocity v sub 2, which is the velocity of the ball at the highest point, must be just enough to cross this point. Once it does, gravity will take over, and the ball will continue its path, completing the full circle. This means v sub 2 must be sufficient to counteract the gravitational pull at the top, ensuring the ball maintains enough momentum to keep moving. The rod is a rigid object that can withstand both compressive and tensile forces without deforming, unlike a string, which can only withstand tensile forces and will collapse if not under tension. We will later extend this example to determine the velocities of the spheres when the rod is replaced with a massless string. With that understanding, let's derive an expression for the velocity of the sphere connected to the rod when it reaches the peak point of the vertical circle. We'll start by considering the situation just before and after the collision of the two spheres, and apply the principle of linear momentum. We can assume the initial velocity of the sphere with mass 2m is u meter per second before the collision, and let v sub 1 and v sub 2 be the velocities of the masses 2m and 1m respectively, after the collision. Using the conservation of linear momentum, we can derive this expression with v1 and v2. Next, we will assume the collision to be elastic, and apply the principle of conservation of energy to both the initial and final states of the system. Since the collision occurs in a single horizontal plane, we will use this plane as the reference level for potential energy calculations, assigning it a potential energy of 0. Since the energy of the system is conserved, we can equate the initial and final energy of the system to derive the second expression. From expressions 1 and 2, we can express V2 as follows. Substituting V2 from expression 1 into expression 2, we can formulate a quadratic equation in terms of V1. When we solve this quadratic equation, we obtain two possible solutions for V sub 1. However, the only physically meaningful solution is 1/3 of the initial velocity. The other solution, where V1 equals u meter per second, corresponds to the scenario where the sphere of mass 2m completely misses the target, resulting in no collision. We will substitute the derived expression for V1 into equation 1 to find an expression for V2 in terms of u meter per second. For the sphere to complete one full circle, it needs to move a distance of 2L against gravity and maintain enough velocity to cross the top of the circle. The total energy at this point, which includes both kinetic and potential energy, represents the minimum energy the sphere must have immediately after the collision. This ensures that the sphere can overcome the gravitational pull and continue its motion to complete the vertical circle. If we assume the velocity of the sphere at the top is v2', we can express the total energy of the sphere at the top of the vertical circle as the sum of its kinetic energy and potential energy. The kinetic energy of the sphere just after the collision is given by this expression. This is at the bottom of the vertical circle, where the potential energy is 0. Since there are no external forces acting on the system, as the sphere moves, mechanical energy is conserved. Consequently, the total mechanical energy at the bottom of the vertical circle is equal to the total mechanical energy at the top of the circle. By combining the expressions for kinetic and potential energy, we can derive a function that relates the velocity of the sphere at the top of the vertical circle to the initial velocity of the 2m sphere. For the sphere to complete one full circle, the velocity at the top of the circle must be greater than 0. If the velocity drops to 0, the sphere will not have enough momentum to overcome gravity, and will fall back down, failing to complete the full circle. Finally, we can derive the requirement for the minimum velocity that the sphere with mass 2m must have to ensure that the sphere with mass m completes a full circle after the impact. This minimum velocity will be such that, after the collision, the velocity of the sphere with mass m at the top of the circle is just enough to maintain continuous motion, preventing it from falling under the influence of gravity before completing the circle. This condition applies only when the mass is connected by a stiff rod, as the rod can withstand both compressive and tensile forces without deforming. However, this condition would not hold if the mass was connected by a weightless rope, which can only withstand tensile forces and would collapse under compression. Next, we will repeat the same exercise, but instead of using a rod, we will replace it with a weightless rope of length L, and find the minimum velocity of the ball with mass 2m needed for the ball with mass m to just complete a full circle. This demonstration shows what happens if the rope is not under tension until the sphere completes a full circle. In this scenario, we cannot apply the same approach as in the previous example with the rigid rod. Instead, we must consider the tension in the rope. For the sphere to complete one full circle, the tension in the rope must remain greater than 0 throughout the motion. If the tension drops to 0, the rope will go slack, and the sphere will not be able to complete the circle, potentially falling under the influence of gravity. To find the velocity of the sphere required to maintain tension in the rope, we can apply Newton's second law to the centripetal force acting on the sphere. At the top of the vertical circle, the forces acting on the sphere are the gravitational force and the tension in the rope. For the sphere to maintain its circular path, the centripetal force must equal the sum of these forces. We can express the tension in the rope at the top of the vertical circle as follows. To ensure the rope remains taut, the tension T must be greater than or equal to 0. This equation allows us to solve for the minimum velocity needed for the sphere to complete a full vertical circle while keeping the rope taut. In the previous example, we derived the expression for the velocity of the sphere at the top of the vertical circle by applying the principles of conservation of linear momentum and mechanical energy, which is given as expression 2. When we derived expression 2, we did not specify whether the sphere was connected by a rod or a rope. Therefore, this expression is applicable in this example as well, regardless of whether the sphere is attached to a rod or a rope. Now, by combining these two expressions, we can determine the initial velocity required for the system to ensure that the sphere with mass m just manages to complete the vertical circle without the rope going slack. The rope can only exert tension, while the rigid rod can provide both tension and compression. As a result, the starting velocity required for the sphere is higher when it is attached to a rope, compared to when it is connected by a stiff rod. With that example, we'll wrap up this video. I hope it helped you understand the basics of impulse and collisions. If you haven't subscribed yet, please do so to support the creation of more videos. Your comments and feedback are valuable for improving the content, so feel free to share your thoughts. I'll be posting a few more videos on this topic, so press the bell icon to stay connected. If you enjoyed this video, please share it with your friends. Until we meet again, stay blessed and take care.